Hello, everyone. Can you hear me? Okay. Hello. Hello, everyone. Hello, everyone. Welcome to our tutorial about hands-on reinforcement learning for recommender systems from Bandits to offline RL with Ray and RLlib. My name is Christy Bergman. I'm together with Kourosh and Avnish, who's in the back. We'll be leading this tutorial session. So before we get into the tutorials, here's a list of links you'll need. I suggest you take a picture and go to that first link right away. That's going to be the GitHub page. That's where you're going to find all the code for this tutorial. And you can also go ahead and download these slides from there. And then the second link is going to be the Q&A doc. Go ahead and start adding questions if you like. We'll try to get to these questions in order. We'll make frequent pauses during the tutorial and try to answer questions that and if there's any questions left over, we'll get to them after the tutorial if we have to. And then the third link, I also recommend that you go to this third link right away. And what you'll need to do is claim a login and pass. And then go ahead and save those somewhere handy for you. I just say do this whenever, sooner than later, because we've noticed with a Google Sheet, when multiple people are trying to edit it at once, sometimes there's problems. So yeah, recommend doing that sooner than later. We're going to be using Anyscale product, and for that, you're going to go to console.anyscale.com when we get to the hands-on part, and then you'll need that login password for that. And the fourth link is to a survey that we would like you to fill out. And please let us know how useful or not you found this tutorial. Hopefully you'll find it useful. Please let us know as we go along so we can answer questions. Okay, so who am I? My name is Christy. I'm an AI ML dev advocate at Anyscale. Before that, I was an SA at AWS. And before that, I was a data scientist building real-time fraud detection. Kourosh will be leading the hands-on part as an ML engineer at Anyscale, working on RL and RLlib. And before that, he was a PhD student at UC Berkeley, working on RL robotics design optimization. So what's Anyscale? Anyscale, we are the original creators and maintainers of Ray. It's an open source unified framework for scalable distributed computing. And our focus is scalable computing for AI and Python. We do it because scaling is no longer an option for doing AI, and scaling is a very difficult task. So our mission is to make scalable computing easy. For companies that don't have to deal with an in-house cloud infrastructure team, we offer managed Ray, which is Anyscale. And these are some of our customers. Some of them have spoken at various conferences, including the Ray Summit that was just a month ago. So thank you to our customers if you're out there. Okay, and this is what we planned for this tutorial. We're going to start with a brief introduction of RL and introduce the RL problem in a formal way. Then we'll talk about recommender systems, traditional approaches, and then how we can formalize recommenders as an RL problem. And we'll introduce an RL environment that we're going to use. Then we'll finish off with online versus offline RL. That's for me, just talking about the concepts, and then we'll go into the coding part. And we want you to get at least two things out of this. What are the advantages of using RL in a recommender system? And what are the advantages online and offline in practical scenarios? Okay, so jumping into the brief introduction to RL, in its simplest form, it's a conversation between an agent and an environment. An agent represents what's triggering action. So it could be a game player, it could be a type of investor, or it could be a type of user on a website. The environment is the agent's world. It's a simulation of the problem to be solved. So the simulator might be of a real physical machine, such as autonomous vehicle. It could be a virtual system like a video game, or it could be a real abstract system such as user behavior on a website. So the environment usually starts off the conversation with an initial state, sends that to the agent. At a particular state, the agent takes a particular action. And after that, the environment gives back the next reward and the next state. Now, behind both this agent and environment is an algorithm. From the conversations, the algorithm has to learn a few things. Number one, how to maximize the sum of these rewards. Number two, how to learn about delayed rewards. And finally, it needs to learn about explore and exploit to maximize learning. So a terminology thing here, you might notice state is what the environment sees and observation is what the agent sees, which may or may not be a subset of the entire state. Another terminology thing you'll notice in RL is this thing called PI, which is a policy. Policy is a function mapping from states to actions. For us, this function is going to be a deep neural network. Policy, you can think of as the RL word for model, but it's a more specific term. It's a model trained on a particular environment. We might use the word model and policy interchangeably, especially when we talk about deploying models. Okay, now that we understand the basics of RL, let's see a more proper formalization. The more formal way is to talk about Markov decision processes, or MDPs, which are stochastic processes that consist of a state, which is represented by random variable S, actions represented by random variable A, and the state transition probability function, which tells you the probability distribution of the values of the next state. The Markov property assumption itself is why we can truncate this to just the values of the previous time step. And think of it as a distribution describing the next state. If I take an action A and state S, what's my next state and what's my next reward going to be? Well, there's also an initial state distribution. Rewards are represented by random variable R. And then we have this thing called the gamma, which indicates how much to discount future rewards. The proper choice of gamma, as you'll see, is a very important part of learning the delayed rewards. So sometimes gamma is referred to as the explorer parameter. In a cat and mouse game, for example, if we set gamma to 0, that mouse is going to either go up or left because it's going to want the immediate rewards. If you set gamma close to 1, then you might see more complicated behavior from that mouse because it knows that there's a delayed reward that it wants to get. Okay, so now that we know, we've seen RL, we've seen the MDP, how can we map recommender system to an RL problem? So for recommender, companies want to recommend content to maximize a user's engagement. In traditional ML approaches or collaborative filtering, you do what we call point-wise filtering. And by that, what we mean is it's static with respect to time, meaning that for a particular group of users and items, we learn what is a certain reward. And in RL, the view is slightly different. We don't consider that everything happens simultaneously, statically. We view it, the RL process itself, as a sequential decision-making process, so that users, as they go along and recommenders, are reacting based incrementally on what they've learned at earlier times. So we believe this is an advantage of RL to apply to recommender systems. Is RL phrases recommender system as sequential decision-making. RL itself has become the de facto ML approach for sequential decision-making processes known as MDPs. RL is useful when there's got multiple goals and possibly long-term delayed rewards. And it's a good fit when you have a traditional ML ranking model, because usually those top K candidates are pre-filtered by that traditional ML model before being handed off to RL. And RL can be plugged in as a last interactive step, either online or offline. So let's talk more about how we can convert this RecSys problem to MDP. So the first step you need to do is to convert each user's session history into a time-ordered sequence of decisions that were made. Documents are often talked about in the modeling algorithm language, but we're going to consider that to be the items that you want to recommend. And the users' items, the users and items features are the states. The recommendations themselves are the actions. You'll have short-term and long-term rewards. And then gamma, as you just saw, it's either 0 for bandits for immediate reward or closer to 1 to train for long-term rewards. And then the agent is going to be in this case, it's going to be the recommender system plus the user. The environment, we're going to use Google's RecSys environment, which is going to be used to convert the user's responses to rewards. And then we're going to use RLlib for algorithms. So let's take a quick look at concepts of an environment you're going to see. So here's the intuition. You're going to start out with 20 items to recommend to a user. User features will be empty just for demo purposes, because in real life, user features are so customized. Pretty much every company would upload their own user features. Item features, we're only going to have one, and it's going to be called sugar. Or we'll call it sugar. And this sugar thing is supposed to help model the idea of a saturation level, that users, if you always recommended the same thing, would eventually get tired of seeing the same thing, and even if that same thing is so great, like kittens or chocolate. So based on the first items, the recommender system is going to select the initial item to recommend. The user is going to respond to that item. And then based on that response, the algorithm using your state action reward is going to update a policy. Possibly step 5, the top 20 candidate items could be updated in DQN algorithms called the target network, which you'll see very soon with Kourosh. The next item is going to be sampled from that policy that you just trained, and the updated recommendation will be made. So now you'll see this thing is looping. It doesn't loop forever. Each loop is called a time step, and it loops up to some specified termination state. Termination state could be the end of a maze, it could be if a player dies in a game, or it could be after 60 videos are watched in a session. So that means time steps or session steps. Another terminology thing is these episode. Okay, so those are called episodes, is the terminology. In RLlib, we call them a rollout. At the end of each episode, a done flag is going to be set to true. The environment API method reset should be called, and that's going to reset that done flag to false. So each episode is many time steps. Now, would you play a game? Think of playing a game. Would you just play it one time? Probably not, because in machine learning, you don't just do something once and report the results. You're going to do it many times to make sure that one time you did it wasn't just luck. So same thing in RL, we're going to train for an iteration, which is going to consist of many episodes. This environment is going to have rewards, immediate and long-term. The immediate reward is going to be called engagement. Kourosh will go into this in more detail, so I just want to touch lightly on here. It's going to be a function of the long-term satisfaction at the previous time step and proportional to the sugar content of the recommended item. And your long-term reward or long-term satisfaction is also going to be a function of what it was at the previous time step, but inversely proportional to the sugar content of what's just newly recommended. And what this RecSys environment is trying to show is that what if your world consisted only of one thing, like sweet chocolate to buy? You might love it at first, but if that's all you ever get to see, eventually you're going to get tired of that, and you're going to have some sort of saturation level of sugar. So a recommender that tries to maximize just short-term rewards would just go for that. Just give you more and more sugar, as much sugar as possible. That's a greedy algorithm. Versus a recommender that tries to maximize the user's overall long-term satisfaction. Its behavior is going to be different. It's not just, it's probably going to give you some healthy kale in there. And then quick word about online versus offline RL. What we've seen so far, we've been talking about assuming that you have access to a live simulator or a live environment where you can freely explore and make trials and errors. Typically, gaming platforms do this. The live environment can be used for simulation, can also be in production. We've seen that. We've seen both cases. And the terminology for this is called, the evaluation during training is called on policy. But in a lot of real world scenarios, you might not have access to that live environment, maybe because the risk of user churn is too dangerous, or maybe because it's expensive, or maybe just because that live environment that you want to simulate is just so complex that you can't exactly specify it, like a lot of real world websites. So these are cases where offline RL is going to be useful. So in offline RL, you train an algorithm based on past agent environment conversations. This data could be log files, of user interactions with items. And it could be from a traditional ML system, in which case you just need to convert the session information into a trajectory of state action reward tuples. The terminology for this, when you do evaluation during offline RL training, is called off policy, because the policy that was used to log that data is different from the policy you're going to exploit data. So RL term is off policy evaluation and counterfactual evaluation. So the benefit of RL is that even though data limitations themselves might limit your ability to learn new behaviors, you can still incrementally improve. So there's an upper bound on this by your data, but you can still improve that data. And you're going to see this concretely in the coding section. So before Kourosh takes over, let me just give you a few words. Are there any questions so far? I covered a lot. I covered the RL concepts into MDPs, and I covered mapping RecSys into an RL. Any questions so far? Okay, we're gonna repeat this stuff in the hands-on. Okay, so, oh, was that, okay, all right. Okay, so now go ahead and open your browser to those logins page, which hopefully you found, and grab your login pass, save it locally, and go to console.anyscale.com. And then you're going to use that login pass to log in there. Does anybody need help with that? Yeah, okay, Kourosh is going to go over this again, so I can go quickly. So after you go into console.anyscale.com, you're going to log in with that. You're going to, in the left-hand side, you're going to see a menu for clusters. Go ahead and click that. And then you're only going to have one cluster. So just click the one cluster. And then you should see a button for Jupyter. You want to click that Jupyter button. The first thing we might need is to open the terminal and do 3 commands, which is ls, cd academy, and git pull. Once you've done that, you can start navigating through the Jupyter notebook. So you're going to click on Academy, and then click on Ray RLlib, and click all the way through to ACM RecSys Tutorial 2022. And then click on Notebook 2, and that's where you're going to be working. Yes.
Hi, I just wanted to ask a question. So it seems like all of the accounts have been claimed. Is there more accounts coming to be able to log in and follow up with the presentation?
Let me see. Yeah, the participation has been more than what anticipated. Yeah, it's going to take some time for us to spin up more, but it's possible. I think so. There is 125 people on Zoom. We probably need maybe 150 more accounts. Yeah. Anything, Alan? Yeah. So yeah, I'm gonna repeat the same stuff on my end, and in the meantime, we're gonna be working on the background, spinning up more accounts. Hopefully, in the middle of the tutorial, we can catch up. They're gonna be added maybe to a second tab here, logins to, and you can go and claim it there. Question in the back? Sorry, what? Yes, I'm gonna go over the same thing. So let me make sure the sharing is properly done. Let me close this. Okay, I need to go to.
Do you actually enter your email, or somebody enters an email and password and then you just put the claimed part?
The claim should be enough.
A few people had a question when you paste your login password. There's going to be a tab password. You'll have to delete that for your login. Okay, so if you grabbed your login password, please leave the Google spreadsheet because it's going to freeze with too many people.
How do I? Where is this thing? Can I get some technical help here with this screen sharing? I want to do an extended mode. So I want to extend this sharing so I can see the same thing over here. Because, yeah, but extended mode.
Duplicate.
Yes, yeah. So displays.
What did you try already?
So I think this mirror. I think mirror should do the work. Yes. I'm gonna try to. So here is the window that you're gonna see when you log in. On the left side, there's clusters. I'm gonna click on that, and there's only one cluster running. So here, down here, there's gonna be a terminal open. So what you're gonna see for the first time that you log in is gonna be on this path. We're gonna cd to academy and then do a git pull. So once you do that, you get a new thing updated on the slides, which you can refer to after this. For the rest of the tutorial, we're gonna be using the notebooks that have been already prepared. Those are accessible by clicking on this. And then once we go in, yes. You're gonna be landed on this initial page. Yeah, then you click on Academy. There's Ray RLlib where the tutorial is gonna go. ACM RecSys tutorial. And here is where you can find all the notebooks. The first notebook, 0, is gonna be just like an overlook over what's out there. There is an introductory notebook that we're not gonna cover, we're gonna skip. This is gonna be a take home you can do later on. It's gonna cover essentially the things that Christy covered, like how an environment is built, some APIs around that, and interaction with it. So we only suggest this if you're a beginner to RLlib. We're gonna go straight to the second notebook, which is more involved. It's gonna be about the RL in RecSys. If you click on that, it's gonna take you to this notebook. So I'm gonna wait a bit more for people to catch up. 2 minutes, yeah, 2 minutes should be. Yeah. I have to shrink the rest of the. I think I have to shrink a bit of the.
Well, you've got at least an hour.
Let's see how it goes. Yeah.
Yeah, you've got at least an hour. You can, like, why don't we ask you? Okay.
So the question is, what was the git pull? In the cluster page, when you enter, if you scroll down, there's going to be a terminal. You can do git pull inside the Academy folder to get the latest version. Okay. We'll try to go a bit faster than usual. An hour 15, but it's okay. So we are at the 1 hour mark. So let's continue. So what we are going to cover in this notebook is like high level wise is 4 pieces of topics. We're going to start with creating an environment in about like this recommendation system problem that Christy outlined first using RecSys. In the second and third part, we're going to use RLlib to run a Bandit as well as an RL algorithm on it and compare them to see which one is better, works better in what situations. And then if you have time at the end, we're going to cover a bit of like offline RL, how we're going to use RLlib to do offline RL, using the log data that was collected with a random policy on the environment we created earlier. So RLlib is a library that we built on top of Ray. It has a lot of pre-implemented algorithms in RL, as well as Bandits, as well as offline RL, that we're gonna get a glimpse of how it's gonna work today. It abstracts away all the compute layers that sit behind it. So you can essentially arbitrarily scale your workloads to many workers so you can get the best out of your compute resources. The notebook is going to be very dense, but at the same time it's self-contained. So you're going to see a lot of text, in between cells. For the purpose of this tutorial, I would just recommend skipping over reading the text as we go and just pay more attention to these cells and that we run and like how the cells kind of execute. There's going to be a lot of to-dos here and there that are going to be marked with capitalized to-do. Some of them are exercises that we're going to wait for the audience to catch up. And some of them are the stuff that I'm going to code here. And I'm going to just like wait a few minutes for you guys to put them in and then execute the cell to see them in action. So let's start. So we're going to run a couple of initial cells, which are about just importing some libraries. Let's see if it works. Everything's set properly. Yeah, it's going to take some time to run the first cell. Yes, so the second cell is about just importing RLlib, which we're going to use, and a couple of helper functions. And the last one is importing RecSys, which is the library we're going to use for defining a recommendation system. Particularly, we're going to import this modified long-term satisfaction RecSys environment, which we have created beforehand. And we're going to inspect this environment and see how it behaves and simulates this kale chocolate situation that Christy talked about earlier. So RecSys is a framework that Google has created that allows us to define arbitrarily complex recommendation system environments that was used to develop YouTube recommendation using RL. You can do some further readings by these links. There's a GitHub page and a paper about RecSys. But in a nutshell, what it provides is an abstraction of these different pieces that you can define a RecSys environment with. So we have a user model, which describes the user profile, a user choice model, which describes how a user would interact with your recommendation system, and a document model, which is responsible for telling your agent what are the available items that you can choose a recommendation from. So we're going to cover, we're going to essentially go through each pieces of these custom environment that we have created earlier and see how each piece kind of, like gives you information about what the behavior of the environment is. So the first part is the document model. In this fictitious kind of environment, we have 2 types of items that we're going to recommend. One is chocolate, the other one is kale. The way that these are represented is by a scalar feature between 0 and 1, where the chocolate ones have a higher feature value, like 0.8 to 1, and the kale ones have a lower feature value, 0 to 0.2, for example. At each time step, you're going to see a list of these items represented by their scalar features. And then your agent is going to look at them as well as the user profile and pick the one that it thinks is the best for that particular time step. So right now, what we're going to do is instantiate the environment by calling this cell. It's not defined. Let's see. Did I not record this? Yes, okay, that was weird. So we have the environment instantiated here. Once we print this, we have a nested list of strings which describe this environment. But at the end, we have this gem environment. So gem is a library built by OpenAI, which allows you to describe arbitrarily environments that needs to interact with an RL agent. There is a link to its API, which you can go check out later. And what we're going to use in this tutorial is essentially 2 API calls. The first one is going to be end reset that we're going to basically use to start the conversation between an agent and the environment. So if you call end.reset, it's going to return the initial observation that your agent is going to get exposed to. So for this particular environment, it's a dictionary of some keys to their values. So user is going to be just an empty array, which means that your users are kind of all identical from your the agent point of view. Then we have docs, which describe what are the lists of docs that you're going to choose a recommendation for. So we have 20 items here, each one represented by a scalar value between 0 to 1, representing their sweetness, sugar level, whatever you may call it. And then we have 2 other keys that I'm going to talk about later. Response and time. The next part is the user model. So users are generally described by a set of vectors representing their user profile that can be or may not be observable to your agent. So for example, those features that are not kind of observable are called latent features. And in this particular environment, what we're going to see is that all the users in the world of this environment are going to be identical from the point of view of the agent, meaning that they're not going to be any different than the other. And what your agent has to do is to look at the interactions that you had, the history of interactions that you had with any of these users, and kind of infer what is the latent state of that particular user. And this is kind of observable by looking at the user key in that observation. And that's going to return an empty array, which means there's difference between any of these users. To kind of like give you a glimpse of what the user state in this environment looks like, you can call env.getUserState, which is kind of a hack because in real world, you don't have access to this variable. But you can see, for example, we have defined a user to be like, how much are they generally attracted to chocolates versus kale by defining some distributions over these interests. And there is this kind of, latent variable state, latent variable of satisfaction, which kind of tells about how much satisfied the user is kind of overall with your system, right? And this latent state of the user can actually evolve as you give like different recommendations, condition on the recommendations that they've been exposed to. So the next part is a user choice model, which basically tells the kind of simulator how would a particular user react to the recommendations that you gave so far. So in this particular environment, we're going to be talking about this reward model, this user choice model a lot. So the way that we have modeled this is that based on this property that giving the same, users are generally interested in chocolates. So if they initially come to your platform, they're going to be happy if you give them a lot of chocolate recommendations, they're going to actually buy them. But over time, this interest can actually degrade. And if you, at the step 3, where you have already gave them 2 chocolates, you see like a decline in their satisfaction, in their engagement, then you have maybe 3 options, right? You could give them again a chocolate, which is not going to make them that much happy. They're going to become sad. You could give them kale, which is sometimes maybe they need a healthier option. They're going to become somewhat happy. But you can also give them a mixture of these recommendations, and that would make them really happy. And the way that we kind of model this mathematically inside the environment is by defining this like initial satisfaction factor, sat at time step t, where every time your user kind of interacts with it, it can actually evolve to get discounted as a function of the amount of sweetness that it got exposed to at that recommendation. So this sigmoid function is essentially a way of discounting over time as a function of the sweetness. So if the sweetness is high, this sigma is going to become like a low number, and then it's going to actually decline, make your satisfaction decline over time. And if your sweetness is low, for example, you gave kale, this sigmoid is going to evaluate to like a larger value, and it can actually grow your satisfaction. The engagement, which is the amount, for example, that users spent on that particular recommendation or something like that, is not only a function of this satisfaction, but also their general interest in that sweetness. So if a user is like, generally interested in sweet stuff, this is going to have a, the term AT, which is the sweetness level that was recommended at that point in time, is going to encourage the reward to go up. And then this satisfaction from previous time steps is going to discount that to the amount that they were satisfied with the entire history. So the goal of an agent is to essentially look at this reward profile and its change over time, and then kind of infer the user profile, their interest, and how it has evolved over time, and what is the best optimal action to apply here. So what we're going to see next is essentially seeing this in action, and how we can actually use the environment we created and inspect this reward profile over time, and really kind of understand the reward behavior. So what we've seen before was end reset. You get an observation. It's going to be like, look like this. So the other thing that we can look at is like response and time. So response is essentially a dictionary which tells you whether the user was engaged at that point in time. So initially it's just like a random number, but like as you keep recommending and then they give you a response back, you're going to see two keys. It's going to be clicking versus engagement. So in this particular environment, clicking is always going to be 1 because we're recommending one item, assuming they're going to click on it. But engagement kind of is a function of their satisfaction and the amount of sweetness that they're interested in. So engagement here represents this reward at that time step for that particular recommendation. And it's going to be a number between -1 and 100, where 100 is like the maximum engagement you can get out of the user. Time is going to represent the time step of the interaction between your agent and the user. And it's going to go from -0.5 to 0.5 to kind of represent the, the history of interaction. So what we're going to do next is to run this environment for a single episode and look at the reward profile over time for a particular greedy strategy, right? So we've seen end.reset before. That's just going to return an initial observation. So what I recommend you guys to do is to follow along with the, these changes that I'm making, so you can execute the cell at the end of this part. So the initial observation is end.reset. Then we have like also this end.step, which is another API in the gym. It takes an action generally, and it returns a next observation, reward, done flag, and info. Now, what are these? So every time you call step, you're going to get one transition in this environment. Action is going to be the item that I'm going to recommend. And next observation is going to be another dictionary like the one you've seen before, representing the changes in the state of the environment, which is going to include a new set of items to be recommended at that time, and the response from your previous interaction. Putting these together, you have to infer, what is the best optimal action that I have to do. So then like this step function is going to also return the reward in a separate variable, which is going to be the immediate engagement at that point in time, and a done flag, which is going to say if this episode was terminated or not. Info is going to just be an arbitrary dictionary representing, some arbitrary knowledge about the environment, which is going to be empty generally. So what we're going to do now is run this for multiple steps, right? So at first, I'm going to make this false. While not done, take some steps in the environment. At the end, assign ops to be next ops, and then report the rewards in this reward. Right now, the only thing that is left is filling out the action, right? So action is still to be determined. So one thing we want to see is heuristically, if I look at this environment, maybe giving the chocolate to this user is always the best option, right? So we're going to try that and report the reward that we're going to collect in this environment, and then compare it to the case that I do the opposite, like always recommending the most better item out of my list of items, and compare them in action, right? So in order to get that, if you look at this observation, it's going to be a dictionary, right? So we're going to index in the doc part. But what we want to do is take the max over all of these documents, right? But it's a special max operator because I don't want to take the max over the keys, but I actually want to take the max over all these values, right? Corresponding to those keys. So I have to define a key lambda function, which is going to be lambda x. So x is going to be each key here. And then, so it's going to be ops doc key and then x. So this is going to, for example, in this case, return the string corresponding to that key that has the maximum value, which is going to be, for example, this 2, whatever, right? So you have to convert that to an integer because it's a string so that this step function can kind of accept that. So now we can run this cell, and then the next cell is going to actually plot this. So what you can see here is that we ran the environment for 10 time steps. So this goes from 0 to 9. This is essentially representing the engagement per time step for this greedy policy. And what we have seen is the reward starts very high because maybe the user was interested in chocolates and the initial value is like 35. But if you keep giving me the chocolate, my reward is gonna like suddenly go down all the way to maybe 1. So you see a massive drop in the reward engagement per time step for that particular user. Now, what I would like to do is to give you some time to fill out the next cell, which is going to be essentially the same thing, but instead of using the max operator, use the mean operator to pick the k-least option, the most speeder option here, and to take a look at the reward later. Let's give it 2 minutes. Yeah, this one. Okay. so let's complete the later part. So here we have to pick the minimum. So I'm gonna just copy this thing. Okay, I've been told that the new clusters have been spun up. Is it on the same thing? Okay, okay. So we're gonna paste this here, and instead of this, use me. Then we can run the cell the same way. So now let's talk about the observations here. The first difference we're seeing is that the magnitude of reward is much lower, like it's around 1, but it's kind of constant. So it goes from around 1 to 1.1. That's like 10% difference. But if you run this maybe twice, it doesn't have a trend in it, right? It doesn't go down or up. Now, what we can be suspicious about is this environment, like this particular user is generally more interested in chocolates because it showed, a 35 value for reward at the first time. But they're kind of desensitized to the kale that you recommend, right? Now, the question is, what is the best combination of kale chocolate recommendations that I can give this user to maximize the output, the engagement over this entire 10-step session? So before getting to that answer, it's always good to run some trivial baselines on the environment, try out different strategies to see what is the kind of magnitude of engagement that you can extract from this particular user or like this environment. So far we've seen two different greedy strategies, one picking the minimum feature value and the other one picking the maximum feature value. And what we want to do next is, for example, try random strategy. At each time step, picking a random item from the list of items and see how that behaves in this kind of a spectrum of policies, right? So this definition, this function definition takes a keyword, random, argmax, argmin, and number of episodes, and then it runs the environment in the same way, right? So you instantiate environment, you reset the environment, there's some metrics to keep track of. You run for several episodes, and then at each time step, you're gonna sample either a random action, pick the argmax, pick the argmin, put them in a dictionary, and then select one based on the string key that we have as input. Run the environment, and then accumulate these episode rewards. So in the end, you're gonna print, the average episode reward across all of these episodes, and then we can compare these different strategies using this baseline function. So what we want to do now is fill out this to-do, which is just picking a random action, what we should do, right? So picking a random action, we have 20 items, right? So that's going to be random rand int 0 to 20, right? One thing to note is that this environment is constrained to always have 20 items in it. So if you pick 1 out of 20, it should just be able to perceive that action. So we execute this cell, and then the way we call this function is by calling it and then passing different baselines, and then storing the final results in their corresponding variable. So we're going to run 1,000 episodes for each of these, strategies. Cool. So let's take a look at results and try to interpret them. So we have first the argmin policy, which gave us an episode reward of around 10. Argmax policy gave us the episode reward of 56, which is around 5 or like 6 times higher. And then we have a random baseline, which gave us a score of 100. The other thing that gets printed alongside these is the satisfaction score, average over all the time steps that you've interacted with this agent, right? So the argmin solution has a very high satisfaction score on average, which means that when it gets multiplied by the reward, you have two things to trade off. Like the higher satisfaction does not necessarily translate to higher like reward, right? So you have to balance this satisfaction versus the sweetness level of items that you recommend. And you can see that as a result, the argmax solution has a satisfaction score of 0.14, which is 8 times, 9 times lower than the other one. Whereas the random policy has a satisfaction that is in the middle, something like that, like 0.5. Whereas like its reward 2 times higher than either of these greedy policies. So now the question really is, if I can do like this good with random, how much can I do better than random, like when I am freely exploring the environment? What is the upper bound of this performance? Okay. So what we're going to do next is try out a couple of baselines here, including Bandits and like a RL algorithm on top of these environment, and see what we can get out of this, how we can improve over the random policy. So I'm going to make a pause here for about 2 minutes. So if you have any questions about the environment setup, please ask now. Question? Yes.
So in this setting, you have a candidate generator. Would you say that your policy is like the ranker?
So right now, yeah, the question is, if you have a candidate generator, can you treat the policy as the ranking generator? So this policy in particular is set up in a way that picks the one item out of these 20 candidates. So you can treat it as the best candidate to recommend at that point in time. But there are ways to kind of massage the policy to kind of like do the ranking, right? So if you give like, you attribute, I don't know, scores to each one, and then you can rank using the score that the recommendation gives.
How do you define a reward? Is it the engagement or satisfaction? So
it's a combination of both. So if you look at this kind of, math here, engagement, which is the engagement at that point in time, is a function of the sweetness of the item, as well as the satisfaction from the previous time step. So you keep giving me the same sweet things, satisfaction is going to go down, but like the AT, which is the adversarial term, is going to go up. So it's not clear where is the kind of like sweetest spot of this trade-off, so you can get the maximum engagement. Let's move on. Can
we take one more question, or do you need it?
Let's keep going. I think we're gonna run out of time. Keep moving. So far we've got here, right? So what we're gonna do next is try out a bandit algorithm using RLlib, which kind of like maximizes an immediate reward. So bandits are classical algorithms and recommendation systems where they optimize this single step objective instead of this accumulated engagement over the user session, right? One way that was described in like the MDP's structure was that if you want to get a short-sighted policy where it just looks at the immediate reward, you can define the problem to be a Markov decision process with gamma equal to 0. What the consequence of that decision is that your kind of policy is going to try to optimize this immediate engagement. Like this mouse is going to just go to this very closest vicinity to look for example, cheese, right? Whereas if you take the same MDP and make the gamma equal to 1 or 0.99 or something, it's going to make that, and it's the optimal policy is going to become this long-term optimization problem where, for example, this mouse now is going to look at, a few steps ahead where if like a huge bucket of cheese is there, even at the risk of getting caught by, for example, this cat, it's going to try to get there. So now the way we're going to apply Bandits is going to treat the MDP to be like very short-sighted, and then take existing RLlib algorithms, like, for example, DQN, which is some algorithm people at DeepMind came up with in 2015 for solving Atari games, and apply that same algorithm with gamma equal to 0 and gamma equal to 1 or 0.99 essentially here. to compare Bandit solution versus an RL solution. So here, in order to do that, we're going to register our environment under this modified LTS name. Then we're going to use RLlib and import the DQN config object as well as the algorithm here. Then what we're going to do is set up the config with the algorithm and other parameters that you care about. So in order to do that, you initialize your configuration and you use the configuration API in RLlib to modify it as we go. So we have bandit.conf, bandit.config.environment in passing the environment name. You can choose like different deep learning frameworks here. It can be Torch, TensorFlow, TF2, and JAX, for example. But for now, we're going to go with Torch. And for Bandit, we're going to choose gamma equal to 0. So let's run this, print this. It's going to be this. Now, what we have to do next is to pass this config object to the algorithm, and they'll tell the RLlib algorithm to run this, and then store the results somewhere. So this is what we're going to do now. There's an API here you can use. So it's written above. So I'm going to just go one at a time. So we need to first create a tuner, which is going to tune this algorithm. We can pass in the DQN, class, which is where the DQN algorithm is implemented. And then for param space, we're going to pass in the configuration, bandit config, but in a dictionary format. So that's going to be this, toDict. Other than this, we also have to pass in a run configuration, which tells the tuner where to store the results, as well as when to stop the algorithm. So we're going to use this line here, run config equal to air run config. And then we can pass in a local, for example, directory here. Okay, code here. So which is going to be like this RLlib notebook, offline RL bandits. So sorry, we're going to make this online RL, right? And then the stop is going to be like how many training iterations you want to run this for, right? Right now, we're going to choose one for the sake of time. And then close this. We're going to call this a tuner. And then at the end, we're going to call tuner.fit. And then put the results into this results bandit. So we can run this. It's going to take some time. What's happening under the hood is a tuner object getting instantiated. It spins up a Ray cluster, which is responsible for kind of distributing your workload across many nodes in a cluster. And because we have one job, it's going to just run that for one iteration. And after it kind of finishes, you can see this print statement here, where it says this job was terminated. It was the DQN unmodified LTS job. The total time that it took was 3.5 seconds. So this is just running this for one iteration because we don't have time to run the full kind of training. There is a script that you can use to run this. So this is going to be a take-home part. So we have a couple of scripts put into like this tutorial scripts folder where you can run like each one at your own time. This is like Python, run this online RL algorithm with like a gamma. And then you can use TensorBoard to kind of inspect your results. So what we're going to do now, next, for all of these algorithms that we're going to run, we're going to jump into our saved results folder and then compare the outcome if you wait long enough. But you're going to, for each one, we're going to just run a shorter version of each algorithm to show that you can actually run in a notebook. But like for getting the full picture, you have to wait a bit. Okay, that's the new thing. I don't know where that came from. How do I? You should drop. Okay, cool. So we can print the results. So after this is done, you can print the results. How do we get it? It's okay. Okay. And then you can also look at the episode reward mean at the end of this one iteration, right? So this is basically running, for example, the evaluation process we saw earlier for 100 episodes, 1,000 episodes, something like that. And then average reward for that after training for one iteration is like 96, right? But we have to look at it after each kind of iteration of training to be able to kind of see where the training is going, okay? So if you run this for one iteration, you can go to the path that was used to save this stuff, right? So it's going to be, for example, RLlib notebook, online RL, Bandits, and there's only one experiment. This is where all these artifacts of that training is getting stored. So you have a params.json, capturing all the parameters that were used to train this kind of trainer. We have a progress.csv, which captures all the metrics that you collected during this process, which we're going to use to kind of show you the final results. And then there's going to be checkpoints, saving every iteration, the checkpoint of that model that was trained at that point in time. And there's this TensorFlow board kind of artifacts that you can use to monitor your experiment. So what we're going to do next is actually going back here. We have a folder called saved results, saved runs, which is basically, for Bandits, DQN, and offline DQN, which we're going to see next. We have saved all these artifacts in a separate folder, put in the GitHub, and then you can basically use Panda data frame to read these CSV files and compare them. Clear? Clear. Cool, thank you. Yeah, how do I? Okay. Yeah. So now we're going to use this Panda data frame read CSV API to get the data frame and print it. So what you can see is that we ran this, using the same script for 666 iterations. And one of the columns here is episode reward mean, which indicates what is the average episode after each iteration. And you can see that it goes from 98 to 56. Let's plot it. There we go. Okay. So this is the Bandit solution. We start from around 100 reward, and then it suddenly drops down to 50 something, and then goes back up. Compared to other baselines we've seen before, we had a random baseline, picking something randomly, that was like around 100. Same ballpark as the initial kind of distribution of your policy. So if you don't have any prior, you instantiate your policy, it's going to be just a random choice over your actions. So initially it's kind of a random policy. But as you learn, you're kind of converging to the sweetest baseline. And why is that, right? Is this expected, right? So this is the question we are trying to understand. And if you look at what we are optimizing, right? This is just optimizing for an immediate reward over the things that you can recommend, right? And since the user is more interested in chocolates, they're going to show more interest in sweet stuff, right? Generally. But as you can see, that kind of optimization problem is going to result into this solution, which is pick the argmax, right? And in order to get some insight, so this is basically talking about that. What we're going to do now is actually load the checkpoint at the end of that convergence, like iteration 666, something like that. Run the episode, run a few episodes, one episode with that policy, and then compare the actions to the argmax policy to see really if these two kind of policies kind of are choosing the same items. So you can load, if you go to Bandits, the parameters are saved here. You can load them. You can construct a DQN object, which is what the algorithm we used. This is going to get printed. We're going to restore a checkpoint. And then this loop is going to run the algorithm for one episode, right? So now, if you look at it, there's a to-do here. We have a Bandit action. and we actually step using bandit action. This argmax action is going to be only used to compare the results of the two, which action is getting chosen, right? So for bandit action, we have to really infer, like do inference on the policy, right? So the policy that is stored is like, it's called bandit algorithm. And then we're going to use this compute single action here to compute a single action given the observation at that point in time. So we're going to use this, and then it has an observation as input. Just to reiterate on this, what we're doing is using the checkpoint we have trained for like maybe a couple of minutes. At the end of that training, there's going to be a checkpoint. We restored our algorithm with it, and then we now do inference on that checkpoint using this API. Let's look at it in action. So between any two consecutive dash lines, we have a list of observations, which are a list of, again, sweetness of these items. Bandit feature value is the choice of the bandit solution among these algorithms, the value corresponding to that, right? And the argmax is the other one. And you can see most of the time, right, almost all the time here, except for example, the fourth time, it's choosing the argmax, right? And because this is a trained policy, so you have independently, autonomously, by just exploring the environment, learn to pick the argmax because the optimization problem was like that, right? Now, next, we're going to actually try another baseline using an RL solution, the same algorithm, DQN, but instead of maximizing with gamma 0, we're going to choose gamma equal to 1 or 0.99, right? Cool. So same thing, we're going to do DQN configs, which is like changing the gamma from 0 to 0.99. We're going to use tuner, tuner, apply it, and then save the results in online RL DQN, train it for one iteration, call tuner.bit. While this is running, this is again for one iteration. If you want to get the full training pipeline going, you have to try this take-home part, which is running the same script as before, make gamma equal 0.99, run it for longer, right? 1 million time steps that we're going to run this. This is going to take about like 4 hours, for example, on these clusters. And what we're going to do now, because we don't have time to wait on this, we're going to actually go ahead and look at the final results we're going to get from these two runs and put them together in one picture. So save results and then plotting. There we go. All right. So what you can see here is the orange is representing the DQN solution with gamma equal to 1. Blue is this bandit solution that had a gamma equal to 0, and then we have the two baselines. What is very interesting here is that because you're maximizing this like future rewards, delayed rewards, the DQN solution can freely explore this environment. And therefore, you can come up with solutions that make a substantial trade-off between the amount of sweetness that you recommend at each point in time step versus satisfaction. And if you look at the final outcome, like after training for 666 iterations and waiting for this much, you're going to get something around like 170 of this, over reward that you can make, which is much, much better than the random policy. Cool. So I think the takeaway so far is that if you're dealing with an environment where there is some notion of consequential decision making, right? Where if I take this action right now, it's going to affect the profile of my user and the engagement. Maybe I have to come up with like ways of modeling this, capturing in a simulator, and then applying RL to it. And there are a plethora of like algorithms you can try out in RLlib, but it's really important to get into that iteration process and try this very quickly on your environment. Where, for example, we demonstrated here very quickly. Now we have about 15 minutes. The next section is going to take about maybe 10 minutes. I'm going to give you like 5 minutes for both break and questions about what we've seen so far. There's a question over there. Yeah, let's see.
So could you explain a little bit more on the that order dictionary structure, like a doc, like all the items, like there are 20, is that a 20 recommended item with different sweetness setting?
Mm-hmm. Yeah. So
Okay.
going back up.
That's at the beginning.
Yeah. So let me find that.
Up.
Yes.
Oh,
so I'm going to explain the order of items in the observation, in a single observation. So you have a dictionary of keys to their values. This is what the information that your agent is going to use to infer the next best action. In this dictionary, you have a user feature, which is empty. So that's going to get translated to nothing. You have a list of docs where each doc is represented by a number as well as, a value, a sweetness value. These are going to get mapped to a list of items where each one is ordered. And then from there, you kind of infer which one you're picking. So the action maps to the index at which that item resides. And then you have, also the previous reaction of the user to your previous kind of suggestion, which is capture, click, and engagement, as well as the time. So all these information are going to get flattened to this vector, which is going to get fed into your policy.
Okay, thank you.
Yep.
Hello. So great presentation. This is a very cool framework. Thank you for that. I have a couple of questions. So one is which bandit is the one that you're showing results for?
So I guess in the literature of bandits, there are a lot of different styles of exploring the environment. One thing we found, you can take an parent optimizer like DQN policy or any other RL algorithm like PPO, anything like that, apply it to an MDP where gamma is 0. And then you get a contextualized bandit using that policy, but also inheriting their exploration behavior. So here we have a DQN exploration, epsilon greedy kind of exploration, plus a policy that is a value function that is just optimizing for this immediate reward, which is going to result in this contextual bandit solution.
Okay, so it's essentially a contextual bandit.
Yeah.
Okay.
Yeah.
And my other question, well, at a high level, in real world scenarios, we get rewards that are delayed rewards. I see that this framework would be more for offline kind of training, and you might get this interactive reward. How would you go about, updating the framework, let's say, to consider something like delayed rewards?
Yeah. So what we've seen here is that the optimizer is trying to maximize the sum of rewards, right? Whether that comes from online or online, that's up to the simulator, right? So you have a simulator which gives you a reward per time step, but the way you're optimizing is for sum of rewards over that user session. So if something is delayed, you're still capturing that, but in many time steps later. So your policy hopefully it's fine. But regarding online versus offline, what we're going to see next is covering offline RL and how we can convert this kind of, peaks, essentially collect data from this online environment, put it in a data set, and then offline RL to it, which is going to do optimize a same policy, but using offline RL. Cool. So let me make sure things still run fine. Okay. So hopefully nothing broke with this error. So now let's get into the offline part. Yes, we're going to cut questions right now. And then if we have time at the end, we're going to come back. Okay. Where is DQN offline? And then there we go. Here. Yeah. So what is offline reinforcement learning, or also known as batch RL? So in scenarios that our colleague mentioned here, there's a lot of times that you don't have a simulator, right? Or running things on simulator, exploring the simulator is kind of expensive because you're actually running in real world. There is this direction in RL where you're going to actually use log of this conversation between agent and environment, where you tried different actions at different observations along with their kind of interaction at that time step, to kind of like learn a policy. So in batch RL, you have a historic data set of recorded interactions in the past in form of observation, action, what was the next observation that you've seen, and then the reward for that time step. All of them are put in a data set, a big gigantic data set, and then you kind of like minimize some loss, something or that can capture what is the optimal policy here. So there are two ways of going about this. One way is simply behavioral cloning, the actions that you've seen in your data set. This assumes you have expert demonstrations of what is optimal at each time step, given the situation that you were in. So in this optimization, you're kind of maximizing the log likelihood of the actions that were taken at that particular time in that data set. In offline RL, you don't simply just imitate this historical policy that they run. You use rewards to kind of supervise which of these transitions is kind of more optimal. So you're kind of imitating the highly rewarding transitions versus downweighting the things that didn't result in a long-term reward. So what we're going to do now is essentially we have created a data set already using the simulator that we had earlier. This is kind of cheating, but like you can use your own like current policies in deployment to collect different policies, right? To collect data from different policies. Here we're going to randomly explore this environment like we did before, and then put all of these data in these transitions into a gigantic data set, and then read that from S3 and then analyze it, right? So this is where the data right now resides. We have a small data set right now for the purpose of tutorial that was randomly collected. By random, I mean we use the same environment, but instead of greedy or like the other greedy algorithms, we ran this random strategy. And then collected these transitions, put them in this data set, and now we're going to read this. So we're going to use Ray dataset to read this S3 bucket and then put that in a Panda data frame and analyze the columns and the first two rows. So each row is essentially a transition from one observation to another one. What was the action that was taken there? What was the reward for that particular time step? It could be 0 and then 1 sometime later, right, for that transition. But right now, this is a continuous dense reward. And you can also have the same done flag, whether this was a termination state or not. Episode ID, which indicates, okay, which user you had a session with and like what type of context was around that episode. The time step that you, like this was taken at, sampled from at that like particular episode, and action probability corresponding to the policy that was used to collect that data. So here, because we have 20 items, things were collected randomly, the action probability is like 1/20.05. So this observation where you see like these strange string is basically a binary version of what we've seen earlier, right? So that was like in a dictionary, you basically compress it in this binary format, and then RLlib kind of read that back during like the iteration over data set. So there is a couple of things that we have to do. So what we're going to do now is apply the same DQN to this problem, but instead of sampling a transition from environment from the actual simulator, we're going to use this data set and treat it as a simulator, right, so to speak, right? And we have to tell the configuration that this is what we're going to do. We're going to, instead of a sampler over the environment, we're going to use a data set and then run the evaluation using the simulator. So every time we train, every iteration we train, we're gonna capture this policy, run it on the environment, and record the results back and report them back. So there's a couple of API changes we have to make on the configuration. First one is calling this .offline data. It accepts a data set key, what is the format, and what is the S3 bucket that we're going to use. It accepts all these like different formats, like Parquet files, JSON, you know, like all these, you know, other common data set formats. We have to describe what is the environment we're going to use during kind of evaluation. But instead of giving the name of the environment, which we have registered before, we have to give it the action space and the observation space, which describes what is the space, like this user doc key kind of format that you expect the agent to kind of digest, and what is the output structure of this policy that you're learning. And that's going to be dictated by this action space. Then we have this .evaluation config, which says, okay, at every iteration, one interval, which means one iteration, run a sampler for like without any exploration on the environment and run it on this modified LTS environment. So here is the config modification in action. Same thing, also making training gamma equal to 0.99 here. The take-home exercise to run is to run this for longer than what we're gonna run, which is one iteration. Now we're gonna do this here. So this script is different than what we've seen before. The previous ones were run online RL. This is run offline RL with the data set suffix, which is this sampled data set, you know, on random transition, which is the bigger version of what we are seeing right now. And once this runs, we have to see, yeah, so terminated. The total times that it took this iteration was 8.2 seconds. And now we can look at the results and plot them compared to what we've seen before, right? So the blue one ran for 2,000 iterations on the data set, right? And what you can see is like a lot of like jumping around early in the training, but like after some time, it kind of learns the kind of delayed reward kind of structure, and then it goes like up, right? Higher than the random baseline that we had earlier. So we remember that we have used the random data set initially, and now we are actually doing slightly better than random after this like many training iterations. This is kind of a promising direction, right? Where you use the current policy that you have in the deployment, collect your data set with it, then apply offline RL to it. You can slightly improve over your offline RL solution, your random policy solution. And then if you do this over and over, you get into this vicious cycle of improvement, right? Where with every iteration, you collect more data, you retrain. Compared to online RL, where you also learn how to explore, this is not going to give you the same result, right? So in the previous online RL algorithm we've seen, if you have a good simulator, this is a takeaway. If you have a good simulator of what's going on, you better use that simulator, because during training, you're also optimizing for this exploration, where it basically explored these different kind of optimization, you know, procedures, like different trade-offs, different levels of trade-off, and then it can come up with the best solution overall. Whereas if you use offline RL, you're kind of limited to the quality of your data set that was, for example, randomly collected, right? And you can slightly improve over that. But this is still better than Bandits because you've optimized this long-term reward even in the offline scenario. Yeah, so that's basically it. More references, like we have a couple of other tutorials. So if this was not enough to cover RLlib, you can this Ray Summit tutorials that covers a lot of like other things in RLlib, like how do you serve parameters, how do you serve your models, how do you train you know, other online RL algorithms, and how do you apply them in different like multi-agent scenarios and things like that. What is that? Yeah, it also covers the basics. And then we have a documentation page on Ray, which you can follow and like learn more about RLlib. In the end, I want to thank you guys for attending. Please also take out this survey that is linked here. It's very important for us to kind of modify our content in the next conferences and make sure it kind of serves the audience well. You can also follow us on these social media, GitHub kind of pages, Twitter, GitHub, Slack, or Discuss forums. And with that, I'm gonna take more questions. Thank you.
A couple questions earlier. But if you have to go, this is the formal end of the session, but you can still stick around if you'd like.
Hi, I have a couple of questions generally related to reinforcement learning and recommender systems. So the first thing is the examples that you showed involved about like 20 actions or 20 different items, but generally at scale of like Facebook or at Google, you have billions of items. So how does this scale with that number of items?
Yeah, good question.
And the second question is also, so in the mouse and the cheese example that was shown, there are restrictions where the reward is delayed because mouse cannot go to the last cell on step 1. It has to cross through a path to reach that step. In recommender systems, you could essentially recommend any item at any time.
Mm-hmm.
So there's no restrictions there in that sense.
Mm-hmm.
So any comment on that?
Okay, got it. Okay, so the first question was how does this approach scale where you have a lot larger number of items than 20? So there are like ways to parameterize your policy to capture that, right? So there's this, for example, paper with DeepMind on how they applied RL to like their Dota game, I guess. There's like a 170,000 actions there that you have to choose from. And you do this in embedding space where you kind of embed each item to this latent vector. And then your policy, instead of picking one, is outputting and embedding. And then you find which one is like better by just doing a inner like cross entropy between these two vectors, dot product, yeah, to find the similarity and then choosing like an argmax over them. That's going to be giving you like out of 170,000, which one is most similar at that point in time, to my thing. The second question was restrictions on recommendation systems. They don't exist, but they exist here. So you can capture these like hard to codify stuff in a like in an environment, right? Where you're, I don't know, like for example, like recommending item 1 is always given, you can recommend it, right? And it doesn't like violate any restrictions, which is gonna be fine. Like your agent learns that at that point in time, this was allowed because I didn't get any penalty or something like that. I don't know if that answers your question, but.
Yeah, so are you saying you can just recommend that item at the step 1 because you can, but then what's the point of using reinforcement learning?
So every time you're gonna see which items you can recommend, right? And from there you can basically, or you can basically contextualize the observation to also include the items that you cannot recommend, right? And then your policy is gonna see that and then act accordingly, I think. And then you can capture the kind of performance with the reward, right? If you recommend something that was not allowed, for example, because you've seen that before, the reward is going to be, for example, low, something like that. Otherwise, you can recommend it and maximize the accumulated reward.
Does any of this support dynamic action spaces? So let's say we started with 20 actions and then we wanted to add 2 or 3 new ones in, we're experimenting, whatever. We want to try, see if the algorithm pick things.
Mm-hmm.
I'm kind of like thinking through this as I'm asking the question, and I'm like, so a DQN, the last layer, right? That's going to be the length of the nodes. I don't know if there's like ways to like add extra layers in or extra nodes in at the end or something.
Yeah, so you can change the architecture of your policy or network to be, for example, these sequential decision-making processes, like, I don't know, RNN or like transformers. And then instead of when the episode ends, or like when the decision is to end that episode by the agent, you're going to inject like a padding, like a very previously determined token, right? That says this is the end of the actions, right? And then you can parameterize your policy that way using that architecture, and then train your model using that. So we allow customized model and customized architectures in RLlib, where you can play around, you know, inject your own architecture, which could cover these use cases that you mentioned.
You can also do the program.
Yeah, so you can also do this like parameterized action space that I talked about, where you have embeddings of actions, and then, you know, doing the dot product is like the scale of how many ever actions you have becomes irrelevant. You and a set of new items, then you do a dot product over that many set of items, and then you pick down argmax again.
Thanks very much for the nice tutorial. I was wondering, you presented an example of a very nice simulator, but was also very simple, and of course. But how, like, I was wondering if you had any thoughts on how to build a simulator to more or less imitate how users really behave in a natural environment. I suppose that's very difficult to do, but do you have any thoughts on that?
So there are ways people do this, right? Like where they train other neural networks that were independently trained on larger data sets, different kinds of behaviors, and then they can use those pre-trained models as part of their simulator, where those models are served, and then you kind of interact with this neural network-based simulator, and then basically do some sim to real kind of idea, where your simulator is based on data. You have a large data set to train on, maybe. And then during interaction, you kind of like restrict yourself to what that neural network tells you, what's the kind of best optimal action. Hopefully this will generalize the knowledge in your data set, the larger data set, to this like subtle situation that you're going to see later. And then you have a policy, like using this method, you're going to train a policy that serves that kind of simulated behavior.
Okay, thanks very much.
Hi, I have a question. I just wanted to follow up on the previous question. You said,
Who's asking the question?
I think it's on Zoom.
Oh, it's in Zoom. Okay, got it.
oh, sorry, yeah. Sorry, I jumped in right away. I was raising my head in the Zoom. So yeah, thank you for the the tutorial. You were saying that you can have a pre-trained simulator according to your data, but then what is the model, the Bandit or the DQ is going to be trained on?
Oh, so using your model that you pre-train, you're either like predicting what's the immediate next reward or something like that. You don't have a policy that maximizes reward over the session. So with this simulator, the hope is that your kind of prediction generalizes to a single step, but you use RL to kind of maximize that generalization over the entire tree.
So it's the RL is more geared towards per session optimization, right?
Yes. So when you use RL, you're optimizing this reward over the entire session, which can be hard to optimize, right? Like because it's delayed.
Okay. Thank you.
Thank you very much. Very good presentation. I'll continue that question about the environment and simulator. So it seems like before we deploy the model into real situation, we can use all different ways to kind of optimize the policy, right? Based on whatever simulation, like data we built to simulate the environment. But everybody knows, like in reality, it's a little bit different when you deploy to the environment. So that's like the RL will continue optimize based on the real like data, real interaction with the user. Or there's kind of just like the other machine learning methodology, you have to retrain based on whatever certain criteria.
Mm-hmm.
Or this is kind of a feature in the reinforcement learning itself will continue like automatically implemented. Could you explain that in a very little detail?
Yeah.
Thank you.
So I guess there are times that your data sets that you initially pre-train your simulator on is not enough for you to have generalization over like different situations you're going to see in real world, right? The way that like people kind of try to do this is to either learn a model that is pessimistic in those situations, which doesn't give like high reward to those situations that are out of distribution compared to what you've learned before. And this is the principle that is used in a lot of offline model-based offline RL algorithms, where you kind of restrict the agent to explore the simulator on the data set that it has covered, right? That it, on the kind of part of the data set that it has enough support for and has seen those situations. And that has a trade-off because you don't get to freely explore this environment, right? Anymore. And you don't see those particular situations that could be highly rewarding or also could be detrimental equally, right? So sometimes you have to make a business decision where, okay, I'm going to try with this, restricted model, which doesn't generalize outside of the scope of this data set, but I kind of, I'm safeguarding against these situations that are going to be bad or detrimental. So that's one way to go about this. And there is also a way of like using ensemble of models, where if the uncertainty of the models over, that thing is going high, right? Which means multiple models are saying, different things about the situation. In those situations, you can actually do like some sort of boosting, right? Averaging across these or like paying attention to the uncertainty across the models to kind of realize if this action is safe or not, right? So this kind of goes into like the topic of safety in RL or things like that, where how do you exploit models and explore the environment safely, where they don't go out of distribution of these like dangerous states. Yeah.
Somewhat related question. I was looking at some of the docs on the exploration API. And does that work for offline RL as well, or is that just online RL?
That's just online RL but during evaluation, if you're evaluating the policy on a simulator, you can apply these exploration layers on top of it, right? So if you have like epsilon greedy exploration, you can train an offline RL algorithm like DQN without any exploration, because the data set is coming from that saved data set, and then apply that layer of epsilon greedy to kind of have some exploration during deployment. And
okay.
Yeah.
And so that I can customize that. I can create my own stochastic explorer or whatever, softmax, whatever I want.
Exactly.
Cool. Thanks.
Just having, thanks again for the presentation. My questions are around trying to actually get this into production. So, and like sort of have it always be there. So the first question surrounds how much data is needed, do you think? I'll give my use case. I think it's like a couple 100,000 users, maybe 30, 40,000 items to choose from. They pick 4 different things a month, and they can continue to pick those things every month. So I'm trying to get a sense, like, how many interactions do you think we need? How would you begin to think about setting up this problem so that we can try to like go to prod?
Yeah, good question. So this is more about, I think, iteration over a lot of like different choices you have. We had like customers coming to us with the same amount of like, I guess, data set requirements, and they could get away with like 1 million transitions, right? But this is very problem specific, and how complicated is the problem? What is the performance that you want to reach to, right? Things like that. But in offline RL, you're kind of bounded to the quality of your data set. And you can only know if you try this, right? You have to take this, for example, RLlib trainer, apply, like run a tuner job with different hyperparameters, scale it up, and then compare them all at the same time on the same kind of data set, right? We have, for example, ways maybe you don't want to deploy this on production to get the evaluation. And then once you get the evaluation, you want to try this, right? We have like off-policy evaluations implemented in RLlib, which allow you to kind of use the data set, like split it into training and validation, and then use the validation part to estimate the accumulated reward, right? That your policy would have gotten if it was deployed. And you can use that metric, for example, to kind of compare these and then deploy maybe the top 3 most promising ones, right? And then use, for example, RLlib serve kind of API to kind of monitor and things like that.
Yeah, I guess another way you might want to think about that is like the data set that you collect. How representative is it of like all the interactions that your users might have with your product, right?
like as you start to approach like greater and greater representation, greater covering, then like offline RL is typically going to work out.
Yeah, I mean, we're in a situation, like, yeah, I gave you the numbers, so we're not like YouTube scale.
Yeah.
So it's possible to like have a data frame, I think that will slow your computer down, but that will have like all the interactions for the last 3 years of like couple and stuff. Some of our products change over time, but generally there's a core to it and they all have similar properties. You know, they're quoted. So yeah, I think we could be in a place where we have most of the data. So I'm just like, if I go to business people and say, hey, I want to do this, I'm just going to kind of construct in my head like the road to like get it out.
Yeah, I mean, people we work with use like daily and weekly data too, and like the number of interactions is like on the level of like what you would see like on like online retail platforms. Yeah,
and they make it happen.
Yeah, I mean, you'll have to try it out, but and they make it happen. They'll retrain like once a day, once every couple of days, or like once every couple of hours.
We do now for like our cyber focus.
Okay.
Yeah. I'm totally ready to do that.
Yeah, I don't think it's a train all 3 years though.
Yeah, no, we don't actually no, we only train on 90 days of data. Like when we train every day at collaborative filter. So we don't think we want to train on more than that because user
changes.
Change. Yeah. Although you feel this magic with these models that you want to see their preferences change over time. So you almost maybe want to reach back a little further in the case of our
a lot of scenarios is that like preferences are cyclic, some of them, right? Every 2 years they have to renew something like that happens with a lot of users. That becomes a pattern that you can use for.
Yeah, so my question is somewhat similar to what we are discussing right now. So it's basically if the environment changes on a frequent basis, right? So because user preference might change, there might be cyclicity in user preference because of some seasonality aspects. So how will RL come into picture wherein there might be cases wherein the policy learn might not be optimal after 2 months. So
yeah,
how exactly can we use
so
RL for this?
there are ways where you can like again modify your architecture to capture time dependency, like historical information. So here use time, right? Time was the interaction index within a user session, right? So the way that you can pick up on that particular feature in the observation is to put that in your observation space. And then when the user interacts, then later into like the history of the information is going to be associated with the time step. Then your model can learn, hey, at this time step I recommended this, and then at this time step I recommended that. The profile didn't like improve, it went down, right? So maybe the user has lost interest in this kind of scenario, right? Let's try something else, right? So it kind of learns to optimize for that particular user based on the historical interaction. So if you modify your observation or like modify your architecture to become this recurrent neural network transformers, which can capture the historical information, then you may be able to capture these changes, sudden changes in behavior toward like maybe my interest profile becomes similar to someone in the past that I've seen before, right? Then you use that as a proxy for where to go.
Any other questions here or on?
I just have a minor question. I think all the good questions were asked. So my question is just about using different types of item features that was also mentioned in the talk. How easy it is to use the framework, for example, to use the image content to build some kind of a sequential visual recommender system. Like the example you were showing was an example of a fashion outfit. And this is a domain where a lot of image content is used. Another application is also in conversation where we could have also these multimodal data.
Yep.
So, yeah.
So the way that we have a lot of like model kind of architecture customizations in the pipeline, right? Where you can essentially, define your own set of encoders which capture the representation of the world at that point in time. So here you have images, you have, conversation, you have other modalities. You can basically come up with your own arbitrary like fusion network, right? Like where you take these convolution neural networks cascade and apply them to your visual representation. You take a transformer, apply it to, I don't know, the audio part, the transcript, something like that, and then fuse them, concatenate them, right? That becomes your encoder of the state at that point in time, and then you put it as part of your policy. So every observation comes in, goes through the pre-processing pipeline, becomes encoded in that latent state, and then you apply your policy on top of that latent state. So all of that is customizable using RLlib. Yeah.
Wonderful. Thank you very much for the complete answer.
Thank you.
Nice talk, Prashant. So my question is related to the action spaces. So is there any kind of number of actions that the RL could help, like have the best or like a good performance in a way that if it's too many actions, would it be kind of the effectiveness will kind of degrade? And second question is, if our action space is actually continuous, will the process be very different?
Good question. So if the action is just like too large, right? It can indeed affect the performance of RL, where you don't learn, okay, what is the proper action at this time? The way you can do that is by reparameterize, like you have to try out different ideas, right? For example, in the case that was earlier, where you have like tons of products that you have to choose, maybe re-rank them, you have to reparameterize your thing, right? Reparameterize your policy to, instead of working on the absolute number of indices in this kind of representation, treat each one as an embedding, right? Treat each item as an embedding and search over the embedding space, right? So the only way that you could think of about on this is like just you have to try, right? There's no easy answer to this question. The other one was what exactly? Continuous actions. So yeah, you can apply continuous policies to this again. Like for example, DQN is about discrete. You have a solve factor critic, which is a continuous policy, but it uses like these Q learning mechanism that is there in the DQN. It uses like soft max over the value function and things like that. There are like other algorithms like PPO, for example, proximal policy optimization. You can use that for like continuous action spaces. So there's a variety of options you have when it comes to even like mixture of policy. Like you have a robotic arm, like you have a gripper, binary, which is binary. So you have to optimize over that, like using a cross entropy loss, and you have like these continuous, joint velocities and joint like things like that. So all them put together is a mixture of continuous and discrete variables that you have to optimize over. These are all possible. Yeah.
All right, any last questions? Folks on Zoom, this is your last chance.
Can you capture them? Yeah, we can. Okay.
All right, thank you so much.
Yeah, thanks, everyone.
I would clap if I had hands free.
Hey, nice to meet you. Kourosh. Yeah. Which company are you from?
Rent. So basically, like maybe next quarter, I wanted to try to be doing, or also basically the application is we have users, they rent. It's like we have 40,000 things to choose. You rent it once, and then you can maybe rent that thing again if you want for a few days. But our goal is to maximize the satisfaction for them, because they need to feel like this is a great membership to have. I'm getting things I want to rent, and then I'll keep paying my monthly